Section 23.5 Homonuclear diatomic molecules. In this section, we will focus on the neutral hydrogen 2 molecule. It consists of two nuclei, nucleus A, nucleus B, and two electrons, electron 1, electron 2. So the distance between electron 1 and nucleus A is RE1. This one, RB1. The distance between electron 2 and nucleus A, RE2, RB2. The distance between the two electrons is R12. The distance between the two nuclei is R, or sometimes we write R sub AB. This is the molecular orbital diagram of H2. Atomic orbital centered on A. Atomic orbital centered on nucleus B. Sigma G, bonding orbital. Sigma U star, anti-bonding orbital. G stands for Garroter, that means symmetric, with respect to the center of the molecule. U denotes Garroter, that means antisymmetric, with respect to the center of the molecule. This is the Schrodinger equation for the neutral hydrogen 2 molecule. We have two electrons. Therefore, we need to include the kinetic energy of electron 1, the kinetic energy of electron 2. The attraction between electron 1 and nucleus A, the attraction between electron 1 and nucleus B. Attraction between electron 2 and nucleus A, attraction between electron 2 and nucleus B. All these four terms are attraction terms, and they are all negative terms. This one is the repulsion between those two nuclei. And I missed one term here. The repulsion between the two electrons. I missed that term. Now let's look at the potential energy surface of the hydrogen 2 molecule. So over here, you have attraction. Over here, you have repulsion. And this is repulsion between the two nuclei. Therefore, this repulsion depends on the distance between the two nuclei. So if we put them together, by the way, this is not just attraction. This is the attraction between the electrons and nuclei plus the kinetic energy of the two electrons. So if we sum up the repulsion between the nuclei, and over here this is the electronic energy, which includes the kinetic energy of the electrons and the attraction terms. So we sum up everything, we get this total energy of this H2 molecule. It does depend on the distance between the two nuclei. So I think when the distance is roughly 1.8 atomic unit, the energy of the H2 molecule reaches the minimum. When the distance is infinity, of course, the total energy is 0. Over here, when the two nuclei are too close to each other, we'll get a very high energy due to the repulsion between the two nuclei. Now let's look at the shapes of the atomic orbitals of two separated hydrogen atoms. So this is hydrogen A, this is hydrogen B. The distance is long enough that these two do not interact with each other. Now let's look at this sigma G bonding orbital. You see the constructive interference in the middle. So there is a significant probability of observing the electron between the two nuclei. But of course, this electrons can also appear here. You can see here, or here, or here. Anti-bonding orbital. Make sure you always draw a planar nodal surface between the two nuclei for the anti-bonding orbital. So over here. Again, the electrons can appear, for example, here or here or here or somewhere here or here or here, here. Look at those dots. But the electrons never appear in this nodal plane. Now let me give you the total wave function of this neutral H2 molecule in the ground electronic state. Quantum mechanical postulate 6 tells us it has to be antisymmetric. So I'm going to write this total wave function as the product of the spatial function and the spin function. In here, the spatial function is symmetric under the exchange of the two electrons. So if you swap 1 and 2, you'll get the same spatial function. No difference. The spin function is antisymmetric. If you swap 1 and 2, you change the sign of this spin function. Right? So let's try this. Let's replace 1 with 2, 2 with 1, 2 with 1, and 1 with 2. And then you get alpha 2 beta 1 minus alpha 1 beta 2. Alright? So you get alpha 2 beta 1 minus alpha 1 beta 2. The sign changes. So again, this is symmetric. This is antisymmetric. The product is therefore antisymmetric. I'll give you another example of H2. In the S1, first excited state. So this is S0. The ground state is S0. So I'm going to give you the notation here. We call that singlet, ground electronic state. When we have this first excited state, one electron occupies the sigma G bonding orbital. Another electron occupies the sigma U star. Alright? And then we need to again construct a antisymmetric wave function. Again, this spatial function is symmetric. If you swap 1 and 2, there's no change to this spatial function. And over here we have a antisymmetric spin function. If you exchange electrons 1 and 2, the sign of the spin function changes. I didn't put the T1 first excited electronic state here. T1 means triplet. So when you have this T1 first excited electronic state, you just need to have a antisymmetric spatial function by replacing this plus sign with a minus sign. And then it becomes antisymmetric. How about this part? Well, it's easy. If you change this negative sign to a positive sign, and then you get a symmetric spin wave function. But T1 means triplet first excited state. So you should be able to write 3 of them. Well, the way to write 3 wave function is this. First, the spatial function is the same. It's sigma G of 1 times sigma U star of 2 minus sigma G of 2 times sigma U star of 1. So minus in the triplet state. Over here, as I mentioned, you can have alpha 1 beta 2 plus alpha 2 beta 1, which is symmetric. What about the other 2? The other 2 are alpha 1 times alpha 2. That's symmetric. And then you have beta 1 times beta 2, which is also symmetric. So as you can see, in the singlet electronic states, S0, S1, you have a symmetric spatial function and a antisymmetric spin function. But in the triplet electronic state, you have a symmetric spin function. Well, actually 3 of them. Alpha 1, alpha 2, beta 1, beta 2, and then alpha 1, beta 2 plus alpha 2, beta 1. All 3 spin functions are symmetric. And then you need a antisymmetric spatial function.